Let us start the session. We are having 2 weeks with us. We will deal with the different methodology for solving constrained nonlinear programming problem. Okay. The constrained nonlinear programming problem, it can be convex nonlinear, may be convex, non-convex optimization problem as well. Now, there are different methodology to solve the constrained nonlinear programming problem. Now, which one is better and which one is the best, that you will understand after a few classes. But if I just start the methods, one is the direct set of methods, another method set is the indirect method. In the direct method, we are having the random search method, heuristic search method, and sequential linear programming, sequential quadratic programming, feasible direction, Zaudensic feasible direction method, that is the gradient search technique, gradient projection method. These are all the direct methods. And in the indirect method, the most popular methods are the interior penalty function method and the exterior penalty function method. And some other variation of Lagrange multiplier method is also there. Now, I plan to have the classes on direct methods and indirect methods, and I will cover a few of them, not all. Now, random search method already I have explained little bit. Okay. On that, the grid search technique, random search technique, okay, grid walk method, that I have already explained. Now, but I will start now sequential linear programming method. That's the beauty of the problem, is that we will consider a nonlinear programming problem, but at every step we will solve a linear programming problem. A sequence of linear programming problem will solve, and ultimately we will get the optimal solution. You must have been studied for the integer programming problem, that is the cutting plane method. If you remember, integer programming, there are two techniques, branch and bound, and the cutting plane method, you must have been covered that one in the previous classes. Now, one of the variation of that only, but here the cutting plane is being formed differently. That is the only difference here. That is why we will consider a nonlinear programming problem. Today I will tell you how to handle the nonlinear programming problem so easily, because we are much more comfortable to solve the linear programming problem. We have several softwares to handle it. We can have a series of linear programming problem, but we will get the solution of the solution. Let me tell you the basic philosophy of this method. Then I will deal with the multivariate nonlinear programming problem, which is of constraint type. Let me consider a nonlinear programming problem where that is of single variable. Let me explain the geometry of the methodology first. See, this is the function given to us, g x is equal to 0, and we are having g x less than 0. That is why this is the feasible space for us. Okay. Now, there is one objective function. This is the objective function, this is moving. These are the level curves of the objective functions, say f x. Okay. Now, only we are having that minimization of f x. X is of this is a linear function subject to g x less than is equal to 0. Okay, this is the only thing we have given. Now, for this problem, one thing we should know, that what is the range of x? We have g x less than is equal to 0, but if we can somehow from the constraint set, we can find out the range of x, that can be nice enough, because we have to start the process from one of the point. What we have to do? We have to consider that the whole thing is included within C and D, say. Okay. Now, say let me consider instead of C and D, A and B. Alright, the first 2 points. The function is in between this. What is being done? We will consider a point A, then we will, this is a nonlinear function g x, but how to make the nonlinear function as a linear function? We know the Taylor series, Taylor's theorem we know. Through the Taylor series, any nonlinear function can be expanded at a point. That is why if I just expand g x at a point x is equal to a, that can be written as g x is equal to g a x minus a g dot x at x is equal to a, okay, plus this square by 2 factorial g double dot etc., etc. Let me ignore all these terms. That is why if I just consider these 2 terms, then you must be understanding this is a constant value, only x is involved here. That is why it will become a linear function, g a plus something, alright. That is why if I consider, then I will get the value here, and this nonlinear function will be approximated with a linear function. Okay. Now, once this is so, now this function is moving, this is my objective function at different point C0, C1 and C2, it is moving. Now, subject to this linear constraint, then where the solution will be? Solution will be at this point. There is no doubt about it. Okay. Let me consider this point as C. Once we are getting this point as at C, again what we will do, at point C we will again expand g x. Then what we will get? G x is equal to g c plus x minus c g dot x at x is equal to x equal to c, ignoring all other term because we want to have the linear function. Then at this point again we will have another linear approximation of g x. Clear? This is the linear approximation of g x through the Taylor's theorem, Taylor series, and the objective function is moving further and further, we will get optimal solution. In this way, minimization or maximization we will handle, okay. But where to stop and everything I will discuss in the next, where we will deal with the optimization problem with several variables together, and we will apply Taylor series for 2 variables, 3 variables, etc. Let me consider the minimization of z is equal to c x subject to g x less than is equal to 0. Now, there is a restriction is that for this method it is called the Cayley-Cutting plane method. The restriction is that objective function must be linear in nature, it has been said. Okay. Now, if we have a nonlinear objective function, say minimization of x square y square subject to x cube plus y plus 3 less than is equal to 0, we can have it. We can make this one as a linear function by considering this way: minimization of f subject to f is equal to x square plus y square and x cube plus y plus 3 less than is equal to 0. You see, this will become a nonlinear programming problem where objective function is of linear type, z is equal to c x, alright. That is why the Cayley-Cutting plane method is applicable as well for the nonlinear programming problem where the objective function is nonlinear in nature. But it has been advised that you apply Cayley-Cutting plane method where the objective function is of the form z is equal to c x, that means the linear, alright. Now, the first step is that if possible find out the minimum and maximum value of decision variables, alright. Now, for example, we are having a problem where the constraint are x1 square plus x2 square minus 25 less than is equal to 0, x1 square plus x2 minus 9 less than is equal to 0. Can you get the range of x1, the minimum value of x1 and the maximum value of x1? What will be the minimum value of x1? Minimum value of x1 would be 5 and maximum value would be 9, because from here we will get 5 and 9. Similarly, we are more concerned about the maximum value rather, not the minimum value, but we will get the range of x. Okay, I will discuss all these things in the latter part. Let me just explain the methodology first. I will apply this one in the problem. Okay. Now, here then what we will do? We will get the optimal solution for the problem this one, where gx has been expanded at a point, at a given point gx1 star. Now, if this is not there, how really we can get the optimal solution? I will just explain to you in the next. Okay. এক কাট এটা হবে না, আমি নতুন করে করব, একটু প্রবলেম হয়েছে লেখাটা। This is the Cayley's cutting plane method. Let me tell you the algorithm for it first, then I will just apply the algorithm for a problem of a specific. Now, there is a problem where we are considering the nonlinear programming problem, but objective function is of linear type. Now, minimization of z is equal to cx subject to gx less than is equal to 0. Now, from the set, if we can find out the minimum and maximum possible value, what are the minimum and maximum possible value of the decision variables? How we can find it? Feasible space only guide us that how the decision variables can move. Now, feasible space, how it is being constructed? This is being constructed with the constraint set. That is why from the given constraint set, we will try to find out that what would be the maximum possible value for the individual decision variable. What is the minimum possible value of the individual decision variables? What is the minimum possible value of the individual decision variable? That is given is 0, but maximum value we will try to find out from the problem. And after that, what we will do? We will find out minimization of z is equal to cx subject to x is varying within that range. Okay, we will get one optimal solution there. Once we will get one optimal solution, let it is x1 star. Next, about x1 star, we will expand the nonlinear function, constraint functions, whatever functions we are having, okay, around that point. Then all the constraints will be converted to the linear constraint, but objective function is linear, z is equal to cx. That is why we can solve minimization of z is equal to cx subject to x within a to b, and this is the function for us. If we solve it, we will get one optimal solution as I showed you. Once we will get one optimal solution x2 star, again we will expand g with respect to that point. Then we will again find out the solution, optimal solution for this. We will add the constraint, this linear constraint in the previous problem, and we will solve it again and again. That means we are putting different cutting planes within the feasible space. In this way, the cutting planes, we will see the process will stop somewhere. For this thing, let us consider one of the problem. Now, let me consider the problem, this one, maximization of x1 plus x2 subject to x1 square plus x2 square minus 25 less than is equal to 0. Now, from here what we can see that the value for x1 here maximum is 5. From the next, the value for x1 is maximum 3. That is why in general we can have the maximum value for x1 is 5, minimum is 0 we have, alright. Now, for x2 the maximum is 5 here, but here the maximum is 9. That is why maximum of x2 would be 9. That is why we can consider that the feasible region, we can have the space feasible region this way. instead of having the feasible space which is bounded by the constraint space, constraints with our intention to make it as a linear function. That is why what we will do, we will formulate the constraint space newly with the upper bound of the decision variables. Then we will have a rectangle. That rectangle will be the bounded rectangle which will contain the whole feasible space. Is that clear? Now, after that our target is to put one by one cutting planes within that space. Now, once we are getting that, we will solve this. Minimization of z is equal to x1 plus x2 subject to x1 less than equal to 5, x2 less than is equal to 9. We will get one of the solution 5.0, 9.0, and objective functional value we will get 14. Okay. Once this is the optimal solution, what we will do? We will consider this optimal solution in the next iteration. We will consider that x0 is equal to 5, 9, and we will first see what is my h1x at this point. h1x at x0 will have the value 81, and h2x will have the value at x0, that is 25. Okay. Now, what is the meaning of it? It means that if I consider this is as optimal solution, then this much of violation I have to accept. Okay. And if I consider this as an optimal solution, this much of violation I have to accept, because my constraint is h1 less than is equal to 0, h2 less than is equal to 0. That means this value is, at this point the value is 81, that means that value is from 0, that is the violation. That is why where is the more violation is there? Certainly in h1 is more violation is there. That is why in the cutting plane what I have to do, I have to put a cutting plane first. At one time we can put one cutting plane only. That is why we have to find out, if I have a set of constraints, we have to find out for which constraint is most violated. Since h1 is most violated, I will expand h1 around this point and I will put as a linear function. At that constraint I will add in the problem. How I will do it? h1x, I am now expanding. It will be h159, that is 81, plus, this is function of two variables, that is why x minus 5, my f function is x1 plus x2, that is why grad f would be 1, 1 transpose. Alright. Now, and if I consider h1, h1 is x1 square plus x2 square minus 25, that is why grad of h1 would be 2 x1 x2 transpose. Clear? That is why x minus 5 grad of h1 at point 5, 9, grad of h1 the x part of that, plus y minus 9 grad of h1 the y part of it at 5, 9. Is that clear? Okay. That is through Taylor series I am expanding. Now, if this is so, this is equal to 81 plus x minus 5 2 x1, the x part is 2 x1, 2 x1 means 5 into 2, that is 10 into 10, plus y minus 9, 5 and 9 at this point the y part is only 18. That is why this will become as 10x plus 18y minus 131. Alright. What is my constraint then? this must be less than is equal to 0, my next constraint. That is why what we will do, we will formulate a function of the problem as maximization of z is equal to x1 plus x2 subject to g1x is equal to x1 less than is equal to 5, x2 less than is equal to 9, and newly I will put 10x plus 18y less than is equal to 131 x y greater than equal to 0. If we solve this problem, this is again a linear programming problem. x1 and x2, it should not be x and y, it should be x1 and x2, x1 and x2, you are right, it cannot be y, x1, x2, okay. Then 10x1 plus 18x2 less than is equal to 131, x1, x2 greater than equal to 0. If we solve this problem, this is a linear programming problem, if we solve it, we will get one optimal solution, that was x0. If I get it x1, we will get at point 5, 4.5, we will get the optimal solution. Again we will see that in this optimal solution, how much violations we have for H1 and H2. Okay? Now, you must be understanding where the process will stop. Once we will see that the constraint is not violated, we can stop it. Okay? Now, if we just proceed in this way, we will find out maximum value of H1x and H2x, two constraints where x is a capital X is a vector, x1, x2 at point 5, 4.5. We will see this value will come as 20.25 and 20.5. What we could see that H2 is most violated constraint here. That is why again we will expand H2 at point 5, 4.5. H2x will be written as H2 5, 4.5 plus x1 minus 5, 2x1 at 5, 4.5 plus x2 minus 4.5, 2x2 at 5, 4.5, no problem. If I just write it down, we will get 10x1 plus x2 minus 70.25 less than is equal to 0. We will add this constraint where? Here. Okay? We will solve this one. If we solve it, we will get another solution, that is x2. The solution will come, I will show you the series of solutions because you will have a feel that here we need to stop. X2. Again we will find out maximum of H1x and H2x at point x2. We will get the value will come as max of 15.4989. What I suggest to you, you should calculate on your own all these values, what I have done. Maybe some calculation variations may be there, you should check it. That is why we could see H1 is more violated. Again we will expand H1 with respect to H2. H1 x2 plus x minus 2.83 2x1 x2 plus x2 minus 5.7 2x2. This is equal to 5.66 x1 plus 11.4 x2 minus 65.4989 we will get. Again we will add this, append this constraint in the previous problem. we will get the optimal solution x 3 in this way. One by one, let me just write down all the solutions for you. 2, 7, then we will get x 4, 2.22, 4.64, and here just to see how the h1 values are changing, h1 and h2. At this point, h1 value will come 2.05, 4.09. The values are reducing. At this point, the values are coming as 458.5684. Here I have to include here, that should be. Then I will get x 5 as 2.25. Hopefully, you could see the values are converging, and max of 0.0434.5325. Again I will add for h2, and if I proceed just to see how what is the value is coming, 2.12, 4.53, and here the max value is coming 0.1530244. Okay. Now, you see h1 and h2 value, if you are satisfied that these are almost 0, you can stop here, but if you are not satisfied, then again you can include the cutting plane with h2. You will see the values for h1 and h2 will reduce further and further. And one thing is that here I have given you the optimal solution after adding this one. Again you have to formulate one cutting plane in terms of h2, here in terms of h1, here in terms of h2, all you have to append one after another, okay, with the original problem. Ultimately, you will get the solution of the problem as this one. Okay. Now, you could understand the advantage of this type of methodology. The methodology is very simple in calculation, there is no doubt about it. Geometrically, it is very nice to visualize. This is another part of it, because we are starting from the rectangle which contain the feasible space. With that we are starting, and we are putting linear cutting planes one after another, and we are reducing the spaces. After that we are converging to the solution. Okay. Now, this is that is why it has been said that it is very simple to handle, and if you want to do it manually, you have learned the dual simplex method. With that, after appending the solution, the dual simplex method will help you to get the optimal solution in a better way. That is why you apply the dual simplex method, and easy to program even, but there are certain disadvantages of this methodology as well. The first disadvantage is that the convexity, if the region is convex, then certainly we will get the solution. But if the region is not convex, for example, the region looks like this. This is not a convex region, because if I add these 2 points, the whole line is not contained within the feasible space. If this is my feasible space, then whatever solution we are getting through Kelly's cutting plane method, that cannot be guaranteed as a optimal solution. That is one part. And another thing, none of the intermediate solutions are feasible to the original problem, because this is feasible to the local problem we are preparing at that stage, and algorithm also exhibits slow convergence, that is also there. You must have been seeing I had to do 7 iterations, and all these iterations always I write simple small programs to do it. Otherwise, I do it with Excel. I do not do by hand the calculations, okay, and I use the lingo as well with Excel. You also do the same thing, and if the size of the problem is very big one, then you must be understand the convergence will be much more slower. That is why this process, though this is very simple, easy to visualize, and that could be a starting point for understanding the constrained nonlinear programming problem, but this methodology is not accepted in general. That is why you must be understanding we need to learn many methodologies together. You want to, if you want to have a rough sketch of the solution, this could be the good start of it. But in the next I will tell you another method, that is a visible direction method in the next class. Thank you very much.